Okay, so we are now in few of the following videos in this statistical mechanics course. We will be dealing with quantum statistics. Quantum statistics. Till now, in this course, we were dealing with classical particles. And essentially, they were, in general, we consider those particles to be distinguishable particles. But we need to make a formalism for the genuinely indistinguishable particles, and that also we need to rewrite the whole discussion on the ensemble theory in terms of the quantum mechanics. So this is what we are trying to do. So this is a relook to some extent. This is a relook into our discussions in the last few videos. So here initially we will be dealing with an ensemble theory, quantum mechanical ensemble theory. We will reach something called the density matrix. So quantum mechanical ensemble theory and density matrix. So this is what we are trying to do. Now for the discussion, you consider an ensemble, right? Like the normal what we draw normally. So here I have various elements within this ensemble, 1, 2, and etc. And I have a microstate or an element which I call as K, and there are scripted number of elements in this ensemble. So that is our assumption. So I assume that script n is much bigger than 1. So script n is the total number of microstates or total number of elements in my in the ensemble which I consider. And also I assume that all the subsystems or all the elements are characterized by a common Hamiltonian. Okay, so these are the assumptions which I make. And now since this is a quantum mechanical treatment, I need to consider some kind of a wave function, right? So at time t, the physical states of various elements can be characterized by a wave function psi of RIT. Okay. So I defined a common format of wave function for the system. So what is Ri? Ri is the position coordinate of the coordinate for the ith element of the system. So it's a variable. It does vary between the microsystems, and that's it. So psi of RIT, and T is the time in which we take this wave function measurement. So which means that if I talk about this kth microstate or the element, I can write down that the wave function corresponding to that as psi k of RIT, right? So so basically psi k of RIT denote the wave function of the system representing kth element or a subsystem, kth element of the ensemble at time t, right? So that is psi k RIT. Now let's utilize the quantum mechanics you must have learned over the time for the rest of the discussion. So how do I write the time variation of the psi kt? For the purpose I will use my Schrodinger equation, right? So the time variation of the psi kt can be represented as h of psi kt is equal to IH cut psi k dot t, right? Differential. This is with respect to time, this differential. So h of psi kt is equal to IH cut psi k dot t. So this wave function I can always attempt to represent in terms of orthonormal functions, which I can write it as, how do you write it? Psi kt is equal to sum over n an kt phi n, right? Let me keep on putting the equation numbers here, which I will need 1, 2. Yeah. So phi n is the orthonormal function, right? So what is an orthonormal function means by if a wave function is orthogonal and normalized, that wave function is called the orthonormal wave function, right? When does a wave function becomes normalized? If psi equal to 1, right? Then that is the point in which a wave function becomes normalized. Basically you take the inner product, right? Psi star psi. For example, inner product is integral psi star psi, some kind of a function. For example, say I take dv or d nu, whatever, and then I can equate that to the delta function, delta mn. Then, right, if you remember that from time since. So psi m star psi n. Say if I take d tau for my psi m star psi m is equal to delta mn. If m is equal to n, then delta mn is equal to 1. Then that function is, and that wave function is normalized wave functions, right? right, if two wave functions are normal, are orthogonal, then psi1 psi2 is equal to 0. Yeah, so just reminded you that you can go back to your quantum mechanics book if you have doubt on what does an orthonormal function means by. Okay, whatever. So basically, phi n is an orthonormal function, and a n k t is how do I define a n k t? A n k t squared represents the probability, right? Probability that a measurement at time t finds the kth system of the ensemble to be in a particular state phi n. So that is how I can define the ANKT. So ANKT squared represents a probability that the measurement at time t finds the kth system of the ensemble to be in a particular state phi n. Okay, so that is it. That is how I define the ANKT. So now what do you do? Basically, I can now try to okay, we will continue in the next video.